Thanks a lot. And so thank you to the organizers for the great hospitality. So I'm going to talk about a project a paper that we put on arXiv a few weeks ago about looking for an entropy that is monotonic along the classical limit theorems of quantum matrix theory. And actually, since the paper contains mostly computations, I'm not going to present the computations. I will try to provide some context and tell you about the story of this computation. So you know Shannon's entropy for random variables, so minus integral of f log f, where f is the density of a random variable. And it was a question of Shannon that the entropy is monotonic along the central limit theorem. Okay, so you have the central limit theorem here that I recall. You have x1, xn, id variables with mean 0 and variance 1. You found the normalized sum. This tends to the standard Gaussian, of course, but what is interesting is it has an increasing entropy. So the observation is that the entropy of yn, the normalized sum, increases towards the entropy of the Gaussian. Also, if there is any question, I mean, the talk is not supposed to be very long, so do not hesitate to interrupt. So this was an open question, and it was only solved less than 20 years ago by Arnstein, Ball, Barth, and Nauer. And before this breakthrough, we only knew monotonicity of the entropy just along a subsequence, okay, because of this inequality here, entropy of y2 being greater than or equal to the entropy of y1, you will have monotonicity along the powers of 2. Okay, but in fact, monotonicity holds for the whole sequence. And just to mention, a few years ago, Thomas Courtade gave a quick proof using a statistical tool, in particular a maximal correlation. Okay. And there are other occurrences of entropy. You may have heard of Sanov's theorem. So Sanov's theorem is about the empirical distribution associated with your variables. Okay. And Sanov's theorem says that the empirical distribution will follow a large deviation principle with a speed n and with a rate function that is actually the relative entropy with respect to the limiting distribution. Okay, so the entropy also appears in this context. Another context is Boltzmann entropy in the Boltzmann equation for an isolated gas. So you consider the density of particles in a gas. So Ft xv is the number density of particles at position x with speed v at time t. And the equation is the following. You have a transport term due to the displacement of your particles, and you have this quadratic term that accounts for the elastic collisions between two particles, one with the. And there is the famous H theorem, which kind of validates the second principle of thermodynamics, that the entropy at time t of the density of particles increases, okay? And it will increases towards the entropy at equilibrium, which is the entropy of the limiting density. And actually here it's also a Gaussian, and it maximizes all possible entropy that are admissible, so that respect the conservation of energy. Okay. And more generally, if you look at a Markov diffusion process, you also have a kind of monotonicity of entropy. So if you look at the ft, the density of your Markov process at time t, then A of ft will also be monotonic and decrease here towards the limiting Helmholtz free energy, which is just minus the Shannon entropy plus this energy term that is no longer conserved. The monotonicity of entropy gives some flavor to this kind of limiting theorems, especially if you think about the proof that is classically taught in University of the central limit theorem, the one with just Taylor expanding the characteristic function. This is not really meaningful. The fact that we have an increasing monotony, an increasing entropy for the central limit theorem is more interesting. Okay, and there is one last example of entropy that I would like to mention, and it's actually related to what's coming next. So it's called Voiculescu's free entropy, and it's the entropy of a self-adjoint operator, and it's written in terms of the spectral measure mu. Okay, so this was introduced by Voiculescu actually in his theory of free probability. So I will recall the correspondence between the two worlds, so the classical probability world that we are used to, and the free probability world that is more algebraic in some sense. So free probability, you can see it as a like algebraic framework for probability on non-commutative variables. Okay, and essentially you can consider it as a framework for random matrices when the dimension tends to infinity. Okay, so where you would have a probability space, a classical probability space, in free probability you have a von Neumann algebra. Okay, and your variables here are elements of the algebra, and they are not supposed to commute. The tau here is a trace on the algebra. It plays the role of the expectation under probability. And since the variables do not commute, you have a whole new combinatorics for the moments. Okay. But you can characterize the distribution of a variable x in terms of their moments. Okay, and in particular, there will be a unique probability distribution that will have the moments of your variable. This is just some representation theorem. So this is a way of defining the spectral measure of an operator. Okay. There is a notion of freeness that is the counterpart of independence. So I will not enter details, but it's really the analog of independence. And because of that, you have also all the tools. In particular, you have the possibility of finding the distribution of a sum of two free independent variables. So it's given by the free convolution. And the prominent distribution in free probability is not the Gaussian distribution, it's the semicircular distribution, and it's operator. So the operator that has the semicircular law as a spectral distribution. And lastly, the role that was played by Shannon's entropy is now played by the free entropy. So yeah, the free entropy is expressed like this: a log of absolute value of x minus y, mu dx, mu dy. Okay, where mu is the spectral measure associated with an operator. Is everything clear so far? So why do I mention this free entropy? Is because it really plays the role of Shannon's entropy in the analog of the central limit theorem for non-commutative variables. So the free central limit theorem is exactly the same as the central limit theorem, except that you don't have independent variables. You have free variables. Okay. And the limiting distribution is not Gaussian, is semicircular. Okay. So the convergence here is just convergence with respect to moments. That's how you define convergence in distribution in a free probability. And just like in the theorem of Einstein, Ball, Barth, and Nauer, it was proved by Schartenko that the free entropy increases towards the free entropy of the semicircular. Last year, or 2 years ago, we gave a quick proof of this fact just by adapting the statistical tool of Courtade, the idea of Courtade on maximal correlation. In particular, we developed the statistical tools like the ANOVA decomposition, for instance. We developed this in the free probability framework, and it works kind of the same as Courtade's argument. And about the same time, Schartenko and Tao extended the monotonicity of the free entropy for n that is not necessarily an integer. So there is a way to define the sum of a non-integer t variables. Okay, so this is the fractional free convolution here. Okay, and when you normalize by square root of t, you can see with the result that the free entropy is increasing for all t. So that was one other occurrence of monotonicity of entropy. And now we ask the question about limit theorems in random matrix theory. Is there an entropy that is monotonic in these limit theorems? In random matrix theory, we consider the empirical spectral distribution of our matrix. So lambda 1, lambda n, A will be the eigenvalues, and we form this measure. So I will state the 3 main theorems of classical random matrix theory using one common matrix as data. So our matrix Xn will be an ID matrix with a coefficient that are centered in variance 1. So there is first so it's not going to be in a chronological order, but there is first this Birkhoff's law, so the theorem of Tao and Wu, which says that the empirical spectral distribution of Xn divided by square root of n, which is the matrix Gn, tends to the circular law, which is the uniform measure on the disk, the unit disk. Okay, so here the eigenvalues are complex and are distributed uniformly in the disk, and this convergence here is with respect to weak convergence of probability measures, and it holds in the almost sure sense, and also for the expected empirical spectral distribution. There is an easier theorem, which is Wigner's law, which is about the Hermitian random matrices. So you can form here the additively hermitized version of the previous matrix. Okay, so Gn plus Gn star over square root of 2. And you have this result that the empirical spectral distribution of Wn tends to the semicircular one. So now the eigenvalues are real, and you have a convergence of random measures on the real line. And lastly, there is Martin-Kopas-Tours law, where instead of the additively hermitized version, you consider the multiplicatively hermitized matrix. Okay, so this will be given by Gn times Gn star here. Okay. And again, now the eigenvalues are supported on the positive half line, and you have convergence of the empirical spectral distribution towards the Martin-Kopas-Tours. So again, the motivation for our work was to find an entropy functional that is monotonic along this theorem. So there is one thing I'd like to mention is these variables are random measures. Okay, so we will consider actually the expected measure, so the expectation of the random measure, that we have deterministic measure that we can plug inside the entropy functional that we consider. So I'd like to argue now why we think Voiculescu's free entropy is a good candidate for an entropy that is monotonic along this limit theorem. So I already mentioned that free priority is linked to random matrix theory, but there is maybe a more convincing reason, is that if you consider Wigner matrices and Wigner matrices that are invariant under the unitary group, then you can find the joint eigenvalue distribution of Wn. So you write the density of Wn, and using the spectral decomposition and computing Jacobian, in fact, the fact that you are unitary invariant allows you to separate the eigenvalues and the eigenvectors, and it turns out that the joint density of the eigenvalues is just given by this density here with this van der Monde determinant. Yes?
Unless V is X squared, it's only case with it's not
yeah, so yes, think of V as, sorry, think of V as X squared.
We should start from that.
Yeah, yeah. Okay. Later I will mention an extension of our question to non-IID matrices. So, but yeah, sorry, yeah, you're right. Think of Vx equal X squared over 2. So you are actually in the Gaussian unitary ensemble, and yeah, the density is well known, and it's this one. And actually, if you deduce the spectral, the empirical spectral, the law of the empirical spectral distribution of the matrix, you get this density. Just writing this sum here in terms of the empirical spectral distribution and putting the determinant, the product here inside the exponential, and this is how the logarithm of x minus y appears. Okay, so in fact, what we can show, and it's proved by Benaros and Guillonnet in 1997, is that the empirical spectral distribution will satisfy to a large deviation principle with a speed n square and a rate function that is given by this. Okay, so this reminds us as a Shannon's theorem, of course, and this rate function is again related to an entropy. It's no longer Shannon's entropy, but it's the free entropy of Voiculescu. Okay? And it has the same form as Helmholtz free energy. Okay. And moreover, we have actually variational characterization of the limiting distributions. So what I mean by that is that we can characterize for instance, the circular law by a maximum principle or a minimum principle here. The circular law will be the unique minimizer of this functional EG here, which is given by minus the free entropy of Voiculescu plus the second moment. Okay. And the minimum is over all priority distribution on the complex plane. And actually, we have a similar characterization for Wigner's law and Martin-Kopastor's law. The semicircular law will be the unique minimizer over real priority measures of this functional, which is the same, about the same, but half of the second moment. And Martin-Kopastor's law will be the minimizer over positively supported priority measures of this functional. Okay, so again, you have the occurrence of the free entropy in this characterization. Okay, so a more precise question now is are these functionals with respect to the tree theorem here monotonic when you plug in the expected empirical spectral distribution? Okay. So this is what we wanted to show. And we did not manage to show it. And it appeared to be quite difficult for us. So we actually focused on G being Gaussian. So X will now be specialized as a matrix with IID coefficients with the standard complex Gaussian distribution. Okay. And actually, to show the monotonicity in this case, we actually computed explicitly these energies, okay, these three energies. So we found that so now Gn is the G libre ensemble, okay, the normalized G libre ensemble, and the logarithmic energy Eg of the expected empirical spectral distribution of the G libre ensemble will be given by this explicitly in n. So 3/4 will be the limiting energy, okay, the energy of the circular law. There is this term here. This term actually decreases as n to the -2 because log n plus gamma plus 1/2n is the beginning of the asymptotic expansion of the harmonic number. So Hn is the harmonic number, and gamma is a last constant that appears in the expansion. And there is a last term, which is the rest of a certain series, which appears in our computation. For the logarithmic energy of the GUI, we have actually about the same expression, but without this extra series. And lastly, for the logarithmic energy of the multiplicatively amortized version, so which is now the Laguerre unitary ensemble, we have twice the previous one. So with this given expression, we can show that, of course, the three sequences are decreasing, okay, and also convex, by the way. Okay, so this is a bit silly. This is how we show monotonicity just by computing exactly what these quantities are. And I should mention actually, so, oh yeah, this is just summarizing the theorem. Okay, these are the three energies that we computed. And the theorem I just stated actually it's three theorems. We have done the computations independently, and the computations are really quite different one with the other. So we cannot really explain the relation between the energy of G libre and the energy of GUI. We don't understand what's the meaning of this term. So this term is the rest of a series that is decreasing like n to the -3/2. And also more interestingly, we did not find a quick and simple proof that the energy of the Laguerre ensemble is twice the energy of the GUI ensemble, the Gaussian unitary. Okay, so in addition to our theorems, we provide also some simulations that show that indeed these energies, they indeed seem to be non-increasing when we take another distribution for the matrix data. Okay, so remember that we take X as an IID matrix, and we consider, instead of complex Gaussian distribution, we considered several other types of distributions, so the plus or -1 distribution, which is this isolated curve here, Laplace density, also some densities that are not log concave, some also heavy-tailed distributions, and they all seem to be non-increasing. Actually, for the Radmacher case here, if you are careful, you can notice that actually the entropy will be always minus infinity, because you have a discrete matrix, and so actually the energy should not be this one. So what we did here with we rejected in the simulations, we kind of conditioned on the two eigenvalues not being equal. So when you compute the logarithm of x minus y, you kind of rejected the realizations that yield infinite entropy. So there might be extensions of our question to some like conditioning event, or say by adding some continuous noise. At the moment, the question is not very precise. Yeah, kind of. This is the additively Hermitized version of the previous simulations. It's also non-increasing. And same for the multiplicatively Hermitized version. And if you look a bit carefully, it looks also that for these models, the energy is twice. So the energy of the multiplicatively Hermitized version is about twice, actually not exactly twice, I think, but about twice the additively Hermitized. And as I said previously, we can extend the question to non-IID settings. You can, I mean, because the result is about entropy of some empirical distribution associated with eigenvalues. So if you have, like, for instance, beta ensemble, okay, these do not come from IID matrix, but you can still consider the empirical spectral distribution of eigenvalues, and here is the expected empirical spectral distribution, and using the three diagonal models of Dumitrio, for instance, we can also simulate these, and we also find some non-increasingness of the energy. And also we have some monotonicity with respect to beta. So it's not only non-increasing with n, it's also there is some monotonicity with respect to beta. So beta equal 2 is the lowest energy, and then it seems to be ordered as with beta over 2 plus 2 over beta increasing. Right. I have plenty of time left. So I will tell you about how we computed this. So why did we choose Gaussian matrix, Gaussian data as input? Is because in this case we have at disposition the expected empirical spectral distribution of this matrix. So for the Gini matrix, the expected empirical spectral distribution has a density that is given with respect to this polynomial, and I mean it may look complicated, but it's explicit. So for GUE, you have about the same density, but with squared Hermite polynomials, and for Laguerre unitary ensemble, you have a density in terms of the Laguerre. Okay, so actually this is quite nice because it reduces the computation of a 2n dimensional integral to just a 2-dimensional integral. Okay, once you have the density, you plug in this expected spectral distribution inside the definition of Voiculescu free entropy, and you can start computing things. There is also a nice lemma that may be of independent interest. is a rewriting of the free entropy. So free entropy, remember that it's a double integral of log of absolute value of x minus y with respect to d nu. Then you can actually replace the logarithmic term by an exponential term. Okay, we just have a more complicated integral, but this will be more suited for the computation because, for instance, in the Gaussian unitary ensemble and the Laguerre unitary ensemble, we have exponential term. The proof is actually simple. So you have this formula, integral representation of the logarithm. So for any a with a positive real part, you can write the logarithm as an integral and involving only exponential terms. And then you use Fubini. You use also this representation of the Euler constant in terms of an integral. And this is basically the solution. Okay, so now we can continue the computation. So think of nu as the expected eigenvalue distribution of, for instance, GUI ensemble. So this one, which is a rescaled version of this. Okay, you have the Gaussian kernel. So if you take p equal 2, you will be able to use properties of orthogonal polynomials or Fermi polynomials, and nice identities to expand your integrals and compute. Okay. And for the Laguerre unitary ensemble, the kernel is exponential minus s, so you would take p equal 1. This is best. And it works. And yeah, we can finish the computations like this. So at some point, actually, we no longer have integrals. Once we have worked enough, we end up with, so if you look at these densities, these polynomials, Hermite polynomials, they have explicit expressions in terms of binomial coefficients. Okay? So if you expand everything and compute the integrals, it's quite of an heavy computation, but at some point you end up with binomial sums. Okay? So for instance, we end up with having to evaluate this kind of binomial series. And actually, these are identities, I mean, sums that people in number theory and combinatorics, they spend their time sometimes to evaluate. But we did not find such a sum in the literature, so we had to come up with an idea to how to compute it. And actually, it was not even clear that there is an explicit expression, a closed form expression for it. Okay, so for the remaining time, I will just tell you the story of about how we started this computation. This is the window of a very famous, quite famous mathematical software. So it looks a bit unfriendly, but you can just ask it to compute things. Okay, you just type in your computation. Okay, and it gives you the answers. If it knows it, it gives you. So I always start with a trivial computation in case it's making fun of me. And actually, you can do more complicated stuff, and you can do symbolic computations. I know some colleagues who did not know that. So you can use indeterminates. You can use letters. Okay, you just put letters. Okay. So for instance, here I am asking it to compute a binomial sum, a simple binomial sum. So the sum of -1 to the k minus 1 n choose k divided by k. Okay, for k from 1 to n. Okay. Does someone know the answer of this? Well, this software does. So this is the sum in a readable format, and actually HN. Okay. And actually, this is a very known identity, in fact, but we also use this in our paper. So let's try to ask it to compute this. Maybe it knows. I don't know. So I define the sequence. So this quantity with respect to n. Okay, so this is this complicated sum, okay, with all these binomial coefficients, and I expanded the odd harmonic number. Okay, so here it's we have the sum over k less than l, and we have the harmonic numbers, the odd harmonic numbers up to l minus k. Okay, so this is how you specify the conditions in the software. Okay, so this is exactly the left-hand side. Okay. So it starts to think. Do you think it will find the answer? Actually, no, it does not. It does not find the answer. You can go to sleep and wake up 2 hours later. It will still be at this point. So, but it's not over. You have to be a bit more. You have to help actually the software a bit. So now I'm asking it to compute the first term of the sequence. Okay, so I'm asking it to compute the 10 first terms. Okay, and it's quite fast. I mean, if you would do it by hand, it would probably take a few hours. And now it's like you want to play a game. So say I'm telling you a sequence, 2, 4, 6, 8, 10, 12. And then I ask you what's coming next. You would tell me 14, right? So let's ask the software what's coming next. Okay. So I'm asking it now to find a function of n, a simple expression of n, that is consistent with the first. Okay. If it were integers, we would look it up at the Encyclopedia of Integer Sequences. But you could also use this software. There is a built-in function in the software, and here I'm asking it to find a sequence, a function that is matching this. And it finds an answer. Okay, it finds this simple expression that is consistent, and actually you can check that if you take more terms, it still match this expression. So this is what we expect to be as the right-hand side. Okay, and here it's a bit cryptic. So Euler gamma is the gamma constant, and polygamma 0n, you have to look it up at in the documentation, but it's just the d gamma function, and the d gamma function evaluated at integers give you harmonic numbers plus gamma or minus gamma. So actually, the gamma will disappear, and we conjecture this. Okay, and the very fact that we were assured that there is a closed form motivated us to compute the sum. Okay, and actually we did not use the knowledge of what the right-hand side should be. Like we could have sort of an induction, for instance, a proof by inductions once we know what to expect, but it doesn't really work because of the quadratic summation. But nevertheless, yeah, we managed to prove this lemma without using the knowledge of the right-hand side, but still using this kind of software helped us a lot in this project. This and this, yeah, but it will be the same as here. I think it would. I think it. Yeah, I don't think I've tried, but yeah, I think it will be stuck because he's trying to evaluate this. Anyway. Okay, I will try it and tell you tomorrow. I will try to tell you tomorrow, but yeah. And anyway, you have to do this kind of stuff beforehand to have a guess. Yeah. Anyway, it will not be a proof, right? Actually, at some point you have really to prove it. So we use some binomial identities to prove this. And actually, the proof of this is use a still just transform. because you see here it's kind of almost a square of a sum. And if you look just at this part, actually minus one to the k of these two binomials, it's defining a priority distribution. Yeah, with some binomial transforms, we were able to compute. Okay, yeah, I stop here.
We have time for questions. Yes, please.
Average empirical spectral distribution. Can you say anything about the expected energy of the empirical spectral distribution?
It's a good question, and at some point during the project, we were not sure which one we did not consider this one, but so in this case, so you mean, okay, there are two ways of defining it. I think you can use the point correlation function or use two independent copies. And I don't know which one is relevant in this case. Because you see, you could use if I find the definition of the entropy somewhere. There, so either you put the random spectral distribution, right? And you put an independent copy. This is what you want to do, and then take expectation. Yes. Or you could have also look at the two-point correlation. So now you don't have independence. You have the two-point correlation. It will also give you something different. But we thought to take first the expectation and then the entropy because it was more consistent with Shannon's entropy. But yeah, we didn't really look at it.
Manju?
The same actually. So this particular one you can get by differentiating the log partition function with respect to beta or something, right? I mean the average of the entropy, if you want to do that.
The partition function, Zn.
Yeah, if
beta.
you differentiate with respect to beta,
Yeah,
log of that, then you can get. So that's different from what you are doing.
Yeah, it's different. Yeah, because when you differentiate with respect to beta, you have the contribution of the particles that are correlated. Here, here they are independent. So the x minus y is really from one with another. And when you do differentiation with respect to beta, you have the other ones. And to eliminate them, it's not obvious.
Other questions? I actually have two questions. So the first in the case of the still invariant ensembles, but where you have a V. So not when you took IID, but when you took
where was it?
Towards the end.
This part?
Yeah, so in these invariant ensembles, where you do have a large deviation rate function, you also have still the expansion in orthogonal polynomials, except it's less explicit.
Yeah.
But
we believe we can do computation maybe in this case.
By Riemann-Hilbert method, that's what I would think. That
What?
By Riemann-Hilbert method, you can get fine asymptotics of them, not going through the combinatorics, but going through the asymptotics of this.
Riemann-Hilbert, I don't know what you mean by that.
Okay, so there is a method to get the asymptotics of orthogonal polynomials.
Okay. Then you don't.
And what I'm wondering is whether at least asymptotically you can show monotonicity for n large.
That's an interesting question. Okay. We should look it up. Yeah, we should.
And the other question is actually for the IID case. It's not clear to me which entropy should you use. if the entries are IID but not Gaussian, we don't have a large deviation principle.
Yeah.
And it's not clear why.
It's true.
So
But
the fact that numerically it happened to be decreasing, this is kind of, so.
well, there is this variational principle. So
Yeah, but this has nothing to do in the case of
I agree.
independent entries.
I agree. I don't know. It seems to be. But this. Okay, you mean yeah. There is something I did not mention. Is so for the Wigner case and the Martin-Cooper case, actually these terms here, this penalization, they are constant, right? Okay, here it's 1 and probably 1 here. It's constant with respect to n. Okay, here it's not, and it's not even clear if these two quantities are of the same order, and it's not clear. So for instance, for Riddhipratim, I don't remember actually. I think they are both of the same order, but I don't know if it's true for general.
No, but what do you mean they are constant? Why are they constant?
Because the trace
on the expected.
Yeah, unexpected. The trace of the Wigner matrix is 1, and the square. Okay. But this is not constant with respect to n, so this is like really the energy that happens. Maybe this is the one that is dominating, and then the free entropy is a bit meaningless in this case for some models.
Okay. One would expect the rate function to look differently in the general case, and therefore, one should expect additional terms. Okay. Anyway. Okay, let's thank the speaker.